on a recording.
Okay. So we'll start again with the first lecture on foundation of gravitational waves. And we have 3 speakers who will be our experts in waveforms and gravitational waves this week. We have Marta, Colleoni, we have Eleanor Hamilton, and we have Anna Heffernan. Well, take it away.
Yeah, cheers. Thanks, Jean-Baptiste, and thanks for inviting us all. Okay, so the first lecture we're going to do is on the foundations of gravitational waves, and this will be myself and Marta. We're all based in the University of the Balearic Islands, and we all have, I decided to put all our LISA hats here. So anyone who's looking to join the consortium is in the consortium. Marta is the Waveform Working Group co-chair. Eleanor is leading up one of the projects on IMRI systematics within the Waveform Working Group. And then, as mentioned previously, I'm on the LISA science team. And a few things I'll be referencing throughout. And these are, well anyone who's from Spain knows you have to always put up your logos. And there's LISA Consortium, and this is the logo for the LISA science team. A lot, at least in my part of today's lecture, I'll be referencing a lot the Waveform white paper, which was organized by the Waveform Working Group of the LISA Consortium, and also the Red Book. And that's an overview of the mission design that ESA asks for all its missions. And that is also on archive. So I'll be referencing the 2 of them throughout. Okay, so let's go on. Okay, so the outline of the course for this week is today we're just going to go over some of the foundations. I'll be just giving a general overview, so it'll be kind of nice, easy breezy stuff, maybe a video, just a general idea of how everything works. So I'll mention, of course, what was already mentioned was that first gravitational wave, and show how it really showed a very nice structure of the waveform. Then how your waveforms can get more complex, how in waveforms how everything is tied to the parameter space, and then tie all that into the LISA science objectives. And then Marta's going to take over and just do deep dive into the maths, which will generally be about the Einstein field equations and how you linearize them. Okay, then the next session will be tomorrow, which is Waveforms 1, and that'll be more on perturbation modeling, so that will be me. And I'll just do an overview of the post-Newtonian or post-Minkowskian approximations and the self-force program. Don't worry, I'll explain what all these are later. And then tomorrow, late afternoon, we have Waveforms 2, and this will be the merger ring down. So Marta will go over quasi-normal modes, and then Eleanor will do numerical relativity. On Thursday, we have Waveforms 3, and this is going to be how you tie all of these things to actually get waveform models that the actual detectors use. And that'll be Marta and Eleanor again. And then on Saturday, you have a hands-on session. So if you want to use the waveforms for LISA, what you do, and how you tie all this in. So this is kind of like going to feed into, hopefully, your data analysis hands-on sessions. Okay, so off we go. Okay, so the first gravitational wave, I thought hopefully this will play. Yes? Wow. Okay, so this was the simulation that was actually done at the time of that first release. And what generally we want to notice here is that it's circular. You have this didn't come out very bright here, but you can see you have a nice, the in spiral part of the wave. It's just where you've got this almost like a sine wave here for circular orbits. So it's very nice. And then as they get closer together, because they're radiating away energy in gravitational waves, so the energy that drives in the in spiral, so they're going to get closer together. They're going to speed up, so the orbital period is going to decrease, which means your frequency is going to get up. As they get closer, then they're going to start merging here, and this is a nice slowdown to see that. And then as they get closer and closer, you're going to have this then explosion where they actually where you make contact with each other, where they freeze and move it. And then once they form a combined black hole, and then you have this kind of ringing down effect. And what was really nice about this is it shows it's going to zoom out. Okay, you see then the gravitational waves have to go all the way out to infinity, which is where our detectors lie. So this kind of shows nicely all the things that this was done by the SXS collaboration. And this shows nicely all the things that we have to do for waveform modeling. So basically you have, like I said, you have that in spiral, which is this. For the quasi-circular, it literally just looks like a sine wave. Then you're going to have the merger. This is where things start really quickening up. Your frequency increases. Then you have this mass kind of explosion, or your maximum amplitude. And then you have the ring down, which you kind of think of as like ringing of a bell. Okay, and so we have in spiral, merger, ring down. And what you'll hear about as this course goes on is, that's why you might hear IMR. You hear IMR models, in spiral, merger, ring down. Okay, so that's the base structure of waveforms. Okay, but there were several things about that first detection that were, okay, first it was amazing because it was a detection. One of the first surprises was actually that it was two black holes. Anyone who was actually around at that time would know that, like, actually everyone was expecting neutron stars. So before we actually started detecting gravitational waves, the expectation was we're going to see more neutron stars, and black holes were going to be the really interesting, rare sources. Now we all know it's the actual opposite. So people were surprised it was black holes. Also, people were surprised by how big they were for something that happened so long ago, which Jean-Baptiste touched on. But what was really nice was nature was very, very kind to us. Because one, they were so massive, they were very loud. So you could almost see them by the naked eye. But also, they were comparable masses. So they were massive, so we could see them, but they were similar masses. They were already circularized, and they had 0 to small spin. And these are all really nice. Now, this is actually, the LIGO detector is zoned in on this part of the parameter space. But what's really nice is these are the easiest waveforms to model. Because when you're building waveforms, like any mathematical modeling, you start with the most simplest thing first. And the most simplest waveform was the first waveform we saw, and we saw it really, really loudly. So nature couldn't have been kinder. Okay, but if we want to build up from that, first things that people started working was like, okay, you don't often see bodies in the universe not spinning. So spin might be small, but it's still going to be there. So we have to go from non-spinning to spinning. And this, depending on retrograde or prograde, it can speed up or slow down your spiral. So it can affect your phasing. Then are your spins going to be aligned or anti-aligned? So at the beginning, when you have spins, you always say, okay, they're going to be aligned or anti-aligned. But then if you want to go more towards generic, you're going to have them non-aligned. And then you're going to have spin precession effects, which also affects your waveform. Then also what you can do is, like I said, the ones that we've been seeing a lot are quasi-circular, which means you expect the orbits to circularize as they get closer and closer together. But what we also expect is you could have eccentric orbits being seen in the detectors, especially if you see more of the in-spiral before they circularize. But also there's this idea of dynamic capture, where you might have a very eccentric orbit, and it doesn't have time to circularize before they merge. Okay, and eccentric orbits can kind of be seen as a beat. So you can kind of think of like, so remember I said that circular one was a nice sine wave, but the beats are more like when the two bodies are close together at your pericenter passage, you're going to have a strong waveform emission, and then as it goes further away, the amplitudes are going to go down. And as it gets closer, it's going to get bigger, and you have more of a kind of a beat to your waveform. So this nice waveform we saw earlier with the first one, as you get more complex, your waveforms get more complex. The other thing is it was comparable mass. And going from comparable mass to large mass ratios is another complexity. And these actually are considered the most complex waveforms. But it has to have all these things together. Okay, so and when you have all of these, then you have your generic waveforms. So a lot of time you hear waveform people talking about generic waveforms, and it means, have we eccentric? Can we tilt the spin? And are we covering all the mass ratios? Okay, so let's move on. So parameter space. So when I was talking about the in-spiral merger ring down, you can kind of think this is a graph you'll see a lot with waveform people. And the idea is compactness here is compactness in the two-body system. So it's like your orbit, right? So out here is where you're in-spiraling. The two bodies are far away from each other. And then they go into their latent spiral, and then they'll start merging, and then they'll ring down. So when you look at this graph going from top to bottom, you can kind of think this is the progression of time. You're in-spiraling, merging, ring down. Okay, across the x-axis is your mass ratio. So here you have comparable mass ratios. So 1, you have the same mass as one over the other, it's 1, so like you have the exact same masses. And on the other extreme, we have extreme mass ratios in spirals. So you might have a small black hole, falling into a supermassive black hole. And that's the background of these slides, because we call those Emery systems. And they're very particular to LISA, because LISA's the only instrument that is capable of seeing them right now. And so you have a little black hole going into a big black hole. And in the astrophysics sessions, I'm sure you'll hear about all the great science you can do with these, as well as all the others. Okay, so let's go into this a bit more, what this all means. Okay, so remember, in spiral merger ring down, so how close they get, and then the mass ratio. And then this was stolen from that waveform white paper, but it was Martin van der Ment who actually did the graph. Okay, so we'll start at the start. In spiral, you can use the post-Newtonian or Minkowskian expansions. So the idea of this is you're doing a perturbation away from flat space-time, which means your metric is going to have your Minkowskian flat space-time, and then you're going to have a perturbation. Now, for the post-Newtonian systems, this perturbation is going to be based on the system velocity compared to the speed of light, so v squared over c squared. Whereas in the post-Minkowskian, you do it with the gravitational potential. So epsilon is proportional to g. And a lot of time you can actually combine these and expand in both. Post-Newtonian, this was the very first way of solving for gravitational waves, is what Einstein used. As Marta will show earlier, but I didn't want to go too much into it, when you do this metric perturbation and you throw it into the Einstein field equations, you end up with a wave equation, which is why we know we have gravitational waves. Don't worry, we're going to share the slides later if people are scrambling to take notes. Okay, so the application, a lot of time people used to say early in spiral, so kind of up here. But one of the magical things that seems to be happening for perturbation theory in gravitational waves is it seems to always work better than it should. Which means when they start, no. Oh, my builds weren't right. Okay. So as you go down here, they thought post-Newtonian kind of cut off, but it actually seems to work much, much better into quite late into the in-spiral. And everyone's like, okay, in English they say, don't look a gift horse in the mouth. You're just like, okay, great. Let's not complain and just accept it. Okay, what also is nice, though, and this is why it's across, you see the Newtonian is, the post-Newtonian Minkowskian is all the way across here. It works for all mass ratios. Which is also very nice. And this will be, I'll discuss more about this in Waveforms 1 at Wednesday, tomorrow morning. Okay, the next area, no. Okay, sorry, just ignore the right-hand side for now. Okay, we're going down here to numerical relativity. Okay, so numerical relativity, the idea is to solve the Einstein field equations exactly for an exact system. So I'm sure everyone knows here when you numerically integrate anything, you're doing it for one particular system. The nice thing about perturbations is you're solving for all systems. You're keeping it analytical. Okay, so you have your Einstein's field equations, and then you have to go something that everyone always, you're like, the whole thing about Einstein is united space and time, and then numerical, you tear it back apart again into a 3+1 decomposition. But the great thing about numerical relativity was they solved that first problem they got the first orbits in around 2005, 2006. So before gravitational waves were detected, thankfully. And it's comparable for comparable masses. So numerical relativity, the cost of the computation scales almost exponentially with mass ratio, right? So you really can't push too far along the mass ratio. And similarly, if you start with your waveforms really, really far out, it's just going to take longer to numerically integrate them to get all the way in. And remember, as you're numerically integrating, you're bringing in errors. A tiny little error in your phase, and that can accumulate and eventually end up with dephasing. So the idea is you don't actually want to start your numerical relativity too far out, because you will have this dephasing build-up. Okay. So it's applicable to comparable masses. That's why I say latent spiral. Like it can work for early in spiral, but you just have this accumulation of computational error. But it also will do your merger and your ring down. Okay, so you have an IMR here. Okay, and this will be discussed tomorrow late afternoon. Okay, so then we'll pretend that this just appeared, and this is the self-force. Okay, so now we go over to more extreme mass ratios. The self-force uses a perturbation in the mass ratio from a vacuum curved spacetime, ideally Kerr. So if you compare that to post-Newtonian, post-Newtonian starts with a flat spacetime and builds it up. And everyone knows with perturbation you have to have a small parameter, which these are two. But for MRIs, what you do is you actually start off with a Kerr black hole or a Schwarzschild black hole, something you know, and you do a perturbation off that. Because, well, you can't see the MRI behind here, but you can imagine that if you're out here in this part of this space-time, and this is the big black hole, and there's a little black hole here, the overwhelming feature of the space-time you're going to feel is going to be that supermassive black hole, your Kerr black hole. And the little black hole going around it is just going to perturb that space-time a little. So the first assumption you make is that, okay, well, my metric is going to be that Kerr black hole at the background, but then a perturbation, and that perturbation will be proportional to my mass ratio, the little mass over the big mass. One of the things about self-force, a lot of time people talk about it like it's analytical, but the fact is you do a lot of analytics to get to nice wave equations, but then you are numerically solving them. But there has been recent progress, which I'll touch on the self-force when we're doing this tomorrow, in some semi-analytical methods, which are nice. Okay, so obviously the application here is going to be extreme mass ratios. And again, you can see this is for the whole in spiral. So you have the in spiral merger. You might also notice I've added in a P here, a plunge, and a ring down. And that's because when you have different mass ratios, you can imagine with the comparable mass ratios, you kind of think of the two of them orbiting in. But when you have an extreme mass ratio, the big guy is kind of sitting in the middle, and the little one is going around. And this will move a little from the impact of the little one. But it's more you kind of think of the little one in spiraling in. And so there's going to be a point where it has its last orbit and then starts plunging in. And then it will merge, and then you'll have a ring down. So as you move from comparable to more extreme mass ratios, you have this extra complexity to the structure of your waveforms. Okay, and again, that'll be talked about tomorrow. Okay, the next area is the black hole perturbation, quasi-normal modes. So the idea of this, again, it's a perturbation from a vacuum curved space-time, but more what you start off as saying, okay, my two black holes have combined now, and I know they formed another black hole, which is a Kerr black hole. But everything's still a bit dynamic, so it's going to be kind of shaking a little. And you think of that shake like the ringing of a bell, you know? When they impacted each other, that's like when you hit the bell, and then you have this ringing down, and these harmonics are modes. And so you have this idea of you have an amplitude and this decaying. Okay, and the main application of this is in the ring down. And then Marta will be talking about this tomorrow late afternoon. Okay, so these are the four main ways of solving the Einstein field equations. What also then can be noted is you have this idea of hybrids. So again, something else that just works out very nicely is that the post-Newtonian or post-Minkowskian methods, they go quite into touching into the latent spiral. Then they do break down, but happily that's where we can really start our numerical simulations without causing too much dephasing, without going crazy in your resolution. So you can actually stitch. So this is the idea of hybrids, where you can stitch your long PN in spirals. It should be in spiral, excuse me, to your NR simulations. And by stitching these together, then you can get a waveform that goes a very long in spiral all the way into your merger ring down. And this is important for things like neutron stars, because we tend to see more of them in spiral. In the ground detectors, but as I'll mention later, in LISA, you'll also see a large part of the in spiral for the massive binaries. Okay, also to be noted is you have this idea of areas of overlap. And what's really nice about these, so here you have post-Newtonian overlapping with self-force. Before, self-force only got out its first waveform in 2021, around Christmas, so really 2022. But before that, there was this idea, because the self-force, when you're actually doing the calculation, is gauge-dependent, which terrifies people. But then when you bring it into the waveform, you get, obviously, a gauge invariant. But before we had our waveforms, no one was really sure what the self-force community was doing. Was definitely correct. So this idea emerged, well, can we compare with post-Newtonian? And then actually a man called Stephen Detweiler came up with the idea that, okay, there are other gauge invariant quantities we could look for, like redshifts, that we can calculate in both and then compare the two. And this worked out really well and was an explosion of work in, like, I don't know, 2016, 17, around that time. But what was really cool is you could actually use the different analytical methods to read off unknown coefficients. So self-force, you do one mass ratio, but you have all the PN or post-Mikhailskian coefficients in that mass ratio. So you could actually read off unknown coefficients. And similarly with using post-Mikhailskian and post-Newtonian to inform your waveforms. So you can find these overlap areas and see where they agree, but also read off unknown coefficients, which is cool with the meeting of these semi-analytical methods. Okay, and then also, yes. Okay, and then also you have this overlap now of self-force and numerical relativity, and people tried to do gauge invariant quantities, but no one could find one that both methods could actually work out. So they had to wait for the waveforms, but then it ended up being a very nice comparison, which we'll touch on throughout the course. Okay, and then the last thing to be noted, oh yeah, I built my things wrong. Okay, so this is all nice how you actually solve the Einstein field equation, but when it actually comes to doing gravitational astronomy, you can't just hand bits and pieces to data analysis people. They'll be pretty mad at you. So what you actually have to do is figure out a way of combining these things smoothly. So you have a nice, so one of the ideas is the hybridization, where you can hand a nice waveform that can be calculated very quickly. So you can't just think you're going to cover the parameter space with, like, here's a bunch of numerical relativity waveforms. They have to be able to run quickly and smoothly cover the parameter space. So the idea then is you have three different methods to kind of do this. You have the phenomenological waveforms, which is the idea of combining post-Newtonian and numerical relativity and the quasi-normal modes together. Effective one-body does effectively the same thing, but a different way. And these two, you can kind of think of them covering up until about here. There's question marks. They are now trying to take mass self-force information to expand more this way. But for now, they're kind of cut off around here, which is fine because right now they're only being used for the ground detectors, and that's around where the ground detectors can see. And then you also have the NR circuit, which is considered the fastest and best one of the lot, but it's like a fancy interpolation of all your numerical relativity waveforms. So it is, it's only used in this part of the parameter space. But it's super fast for the data analysis people to use. Things have to be able to run in like milliseconds. Okay, so that's the overview of the parameter space and how everything works. So next, we'll go into, I'll touch on the Lisa science objectives and how these waveforms parameter space for each source. Okay, so Lisa science objectives. Anyone who ever read the Red Book? Objective 1 is study the formation and evolution of compact binary stars and the structure of the Milky Way galaxy. Okay, so what they're basically saying is, if this is your response or the noise curve of our Lisa detector, so you have the frequency of the waves you're going to be able to see and how the strength of the strain. Okay, so here's our curve, and all the binaries are kind of sitting around here. So it's predicted that we'll have 10,000 detectable binaries here. There's going to be a foreground of even more that we're not going to be able to resolve, and they're going to form this background confusion noise that it's actually going to bump. So this is actually what the detector can do, Lisa, but then you're going to have this confusion noise that we can't get rid of from the background. A lot of these are not going to be detectable by electromagnetic radiation, but some of them are, and some of them already have been. So this brings in the concept of the verification binaries. So a lot of these are mostly white dwarfs. And then people have been saying maybe 100 when a neutron star or black hole, but apparently this number is shrinking, so maybe 10 to 100. But the verification binaries are white dwarf binaries that have been seen and are being constantly observed by astronomers. So we know where they are. We know that LISA should see them. And we actually have a lot of information from the EM community on where the frequency of what they're gravitating. We can use their observations to figure out the frequency of the gravitational wave they'll be emitting. Now, as it turns out, because these are very far apart, they're very, very early on in the in-spiral, you don't even take in the time evolution of their spiral. You think of it as a monochromatic signal, which is why they're kind of dots all over here. They're not waves going down. And the verification binary, so that first year that Jean-Baptiste mentioned earlier, the reason it exists, that we get that proprietary data for 1 year, not we as in consortium, but to be selected group of scientists, is because they think they'll need a year to verify that LISA's working. And verifying means actually hunting down these verifiable binaries. Because you've seen them with EM, and then you're going after them with your gravitational wave detector. Hopefully, they should be where you expect them to be, and once they are, then LISA gets to go ahead, and it's verified that it is working as expected. Then there's going to be a lot more of them from our galaxy. There's lots of science you can do into this. I'm not going to go into too much because I think your astrophysics lectures will do that. But you can look at kicks and common envelopes, and they'll tell you about formation and evolution channels. Formation and evolution channels is just telling you how the binary came together. Did they just meet randomly, or did they grow together, things like this. It'll also tell you if you're being able to, distinguish this amount of binaries in our galaxy. That's going to tell you a lot about the mass distribution, because you're going to be detecting these the whole time LISA's turned on. So hopefully you get a good idea of where they are in the sky. And also, it can give you information on mass transfer. So white dwarfs, if they get to a certain, within a certain radius, they might start transferring mass and also have tidal effects on each other. So there's lots of stuff we can get there. And then, like I said, this ties in, you're looking at this part of our parameter space. Okay, so what's nice about these, I've stolen this from the waveform white paper. So the idea is here, I'm just going to tell you the status of the massive, I didn't change that. That's supposed to be galactic binaries, ignore that. I'll change it before I put up my slides. Okay, so where are we on these? So when we were doing the white paper, one of the ideas was taking information from what people have observed from the astronomers to what astrophysicists what they think, how things are going to evolve, to actually figuring out what are the parameters that the waveform people need to focus on. I mean, the plan is we want generic waveforms. The reality is that's difficult. So if we have to drop something, it would be nice if we knew for each source what are the expected parameters. Of course, that would introduce some sort of bias in your data analysis, so it's not ideal, but if we have to pick and choose, it's good to know. But it's also good to know that we're covering the expected parameter space. So for each of the sources, we just wanted an idea of the parameter space. So we asked a lot of astrophysicists this question. And basically, this is what we came up with. So you have the binary white dwarfs, the white dwarf neutron stars, and the binary neutron stars. You have the total masses of the system. And these masses are fine. We can take care of that. You have the mass ratios. The mass ratios for these are kind of comparable to maybe 10. With current gravitational waveforms, that's fine. That's kind of covered. Eccentricity, yeah, if it's low eccentricity, we're good. If it's high eccentricity, maybe not so good, depending. What did I say here? No, I said we're good. Okay, never mind. I mean, they're they're expected to be circularized. That's the expectation. But if there is high centricity, those kind of waveforms are just now coming up. But we're not expecting it to evolve too much. Okay, and then the signal to noise mass ratio, I'm not going to talk about much because it's more of a data analysis problem. But as you could see, there's a lot of these, and you have to be able to pick them up and figure out your confusion noise. So that's an ongoing part of the global fit, which I do not know much about, and so I'll leave it for the data analysis people. Okay. Caveats? Yeah, that's the question?
Do you have questions right now?
Yeah, just shoot them on as you go. Oh, yeah, okay. I don't want to hit someone in the head.
Thank you. Quick question, because the eccentricity part here. You had mentioned that these white dwarfs can be almost approximated as monochromatic sources.
Yeah.
Is that, it's a stupid question, but what at like high eccentricities and relatively high mass ratios of like, let's say 4, which is within the range that we're considering for double neutron stars, I guess. Okay, double white dwarfs.
Yeah.
You don't expect them to be eccentric then, the binary white dwarfs. Because
I mean,
I'm asking,
people right now are saying you're not expecting it.
What if there's like a kick? What if there's like a supernova kick? Or, well, no, there wouldn't be, but.
Yeah, I mean, this is why the white dwarf neutron star and the binary neutron stars, they're allowing for eccentricity. But I think for the binary white dwarfs, yeah, I don't. The astrophysicists were like, no, we're expecting these to be circular at this point.
That's a bias, right? Or you
yeah. Well, that's what I'm saying. Like, the whole idea is you really want to be able to detect anything, but also you're informing your ideas from what we've already seen in the galaxy. Yes, go. Always have.
Because in Morito dataset, so the next similarity dataset we were working on actually, we were wondering whether we should add some eccentric system, and there are some simulations of galaxy-like, sources, but they say that there are very few that you should expect to be eccentric, and even these few ones, they should be out of band of LISA because they're very far away. And they get very close, so we might get some bursts every 40 years or so. But there are not very much LISA sources, and there are very few in the models.
Yeah, so then the idea is by the time they get into LISA band, the eccentricity should have it circularized within that radius. Yeah, go for
very quickly, but if they do have eccentricity, you'd expect F double dots as well, like those terms as well. You'd expect it.
I think the few which you can get in simulations, they are so high. Okay, so it's either very zero, no eccentric, or very very high eccentricity. Because I think the few systems where you get eccentricity, you have there's triple systems, and there's something like destabilized, and you have very eccentric systems. So in the last simulation that was out like a few years ago, it was either highly eccentric or zero eccentricity. And if they're highly eccentric, then they just you get to the periaster every 40 years or 50 years. So you see a burst every 50 years, so it's not very good for LISA. I think that's the idea.
Any other questions? Okay. Thank you, Owen. Okay, and then the caveats here that are still up for grabs is there are still a lot of people working on things like mass transfer, how would that affect the waveform, or your F dot, F double dot, and tidal effects. So when people say it's going to be a monochromatic signal, this was 20 years ago when people started saying that. And now, of course, everyone's like, how sure are we about that? Because there's lots of scaling arguments that have been done before. And then when you actually go out and do it, you find, oh, actually, maybe we might see a frequency evolution. We just haven't made our modeling more realistic. We have to make our modeling more realistic. Okay. Sorry, I've gone over. Okay, we'll go. Okay, science objective 2 is trace the origins, growth, and merger histories of massive black holes. Okay, so the idea of the massive black holes. So from a modeling perspective, these are actually kind of like the ones we're seeing now in the ground detectors. They're just bigger, but they're expected to be more comparable mass. And they're going to be absolutely huge, so 10 to the 4 to 10 to 7 solar masses. Astrophysics you could do would inform higher arcal growth, because you actually are going to see mass ratios of 1 to 10. Some people even say 100. But the idea is you're going to see them of different sizes, which is going to be very interesting. Hopefully a few per year. Again, this is saying a few, up to 100, but the bulk should be less than 10. Expected high eccentricity, so this idea that two galaxies kind of randomly come upon each other, there's no reason why they should be orientated the same way. So you can imagine that if there's almost like a dynamical capture, so they're going to come in, capture each other, and also maybe misaligned. And obviously, if you're tracking these, you're getting a population census of the massive binaries of our universe. They also will stay in the LISA band for different times, depending on their masses. So you can have them maybe in 10 hours. They might be a day, a month, or they even be a year. And this is all depending on how heavy they are. Okay, and where this is, like I said, this is going to be in the same kind of area that we use for the ground detectors now, which is the current waveforms that we do use. So it's going to be in spiral, into your merger, and ring down. And then, one of the things to be noted here, which is terrifying. If you play, the problem with these is that they're going to be so loud. So obviously with physics, you're like, oh my God, we've got this insane signal noise ratio. This is amazing. We can do much science. The problem is everything else is underneath that signal. So these signals, you're talking possibility of 1,000 signal noise ratio. So when people are kind of looking about, okay, but if we model this, and this also comes into the complexity maybe of doing higher masses, what happens is, so the idea of here is, Deborah Ferguson did this, for the waveform white paper. If you have all modes, high resolution, and then blue is all modes with the lowest resolution, and the red is the model of the 2-2 mode, just the first mode, the dominant mode. And if you look at it, you're like, oh, they seem to be doing okay. But if you subtract one of the less good models from what you consider to be like all modes at high resolution, your residual destroys everything else that's sitting under here, right? So if you don't get these binaries really exact with your waveform and subtract them properly, you've lost all your science that's sitting under here because you've poisoned the other waveforms. And this is it less so. Well, you can see this is SNR N976. If you have a signal noise ratio of 200, okay, it's not as bad. But if we see something like this, okay, people will be like, oh my God, we can do tests of GR with the ring down. It's going to be phenomenal. But if you don't get it right, you've drowned everything else out. And so these are a problem. It means there's a lot of pressure on waveform people to get highly accurate waveforms and data analysis people to figure out best how to solve this. Okay. So, sorry, I'm supposed to pass to Marta already. Okay, massive binaries. Okay, so where are we? Let's just go through this fast. Total mass in detector, okay, kind of, but just means highly accurate. Mass ratios 1 to 10, that seems to be okay where we are. Dimensionless spin aligned are okay, but spin off aligned, not so, only if they're circular. Eccentricity, there's only some eccentric waveforms now coming out that are used with the ground detectors. And signal noise ratio, again, like I said, this causes a problem that has to be solved by having extremely accurate waveforms and working with data analysis people. And of course, then the caveat here is it's easy to say, oh, well, we've got highly spinning and precision, like inclined spins, and we've got eccentric, but you need a generic one that does both of these. And that doesn't exist right now. Which is fine because the ground detector isn't seeing any of them, but eventually you're hoping that they are, and we are expecting LISA to see them, so work in progress. Okay, and this is that whole idea where, because I've seen some reports when people talk about the science that LISA needs and the things that needs to be done, and you do see the statement written that the waveform problem is solved. Because they're like, oh, we're detecting waveforms and we're doing this already for the ground detector, and it's so far from solved, as you see here. Okay. Extreme mass ratios and intermediate mass ratio spirals. Okay, these are objective 3 properties and imminent environments of black holes by using these extreme mass ratios. A little black hole fall into a big black hole. And intermediate mass ratio and spirals, which are slightly less massive systems. Okay, MRE's the mass ratio, you're talking 10 to 5, 10 to 8. You could get environmental information. It can tell you about the evolution. Eccentricity and spin will tell you about formation channels. We think there'll be at least 1 or 1,000 per year. And again, is 1,000 amazing? Kind of, but then actually you're going to have an Emery background noise, which could prove problematic. If you get a high SNR one, you're going to get really good sky location. And this means you can do things for the cosmic, constraining the Hubble constant. Okay, and then IMRIs is at mass ratios 10 to 2, 10 to 4. These are interesting because to have this mass ratio, it means you need an intermediate mass black hole, and there's still a question mark of whether these exist. And you can have light ones, which would be seen in the ground space detectors as well. And if you get a binary that goes from space into ground detector, you just get a whole lot more science on it. And then heavy, if you get a heavy one, so that's an intermediate going into a supermassive, where a light one is a kind of something that LIGO sees going into an intermediate one. You can get information on secondary spin. Okay, and then this is obviously this part of the parameter space. Before, the idea of IMRIs, nobody really knew how they were going to be solved, but with recent work of the self force, comparing with numerical relativity, it looks like, at least for the more simplest cases, between them they can cover this space. Okay, and then this is like one Emery, but it's different harmonics and where they'll sit. Okay, and then, this will go just quickly. Mass, yes. Mass ratio, cool. Spin, Centricity, no. No. SNR, it's hard. Same for the Emerys. Nope, nope. Yeah, hard. Okay. Understand the astrophysics of stellar mass black holes. There was a lot of excitement around the time GW150914 was detected because Alberto Cesana did this lovely paper where he showed if that binary if it had happened when LISA was flying, LISA would have seen it first and actually would have been able to forewarn the ground detectors, hey, in a week, you're going to see this. And then you can map the signals together and go, wait, was it eccentric in the LISA band and then it circularized, or was it circular all along? And then by doing this, you know how it formed or how it grew. And also you can do better constraints on beyond Einstein. Okay, so yes, they're thinking, well, this number keeps reducing, so let's not talk about that. And centricity will inform the formation channels, and you could also have environmental and center of mass acceleration. And these are obviously in this parent stability mass gap, which is always interesting, that you have 2 mass gaps in black holes, one between neutron stars and little black holes, and one between the kind of stellar mass black holes that we see with the LVK and the supermassive guys we see in the galaxy, that intermediate mass black holes that, like, how do you get from little ones to big ones with no medium ones? And no one's really sure, so you assume they're there, we just don't see them. Okay, and this is here. Okay, because they're not gonna merge. They'll merge in the LIGO band. Okay, and then again, let's just go quickly. And everyone's like, oh, well, these are the LIGO ones we know about. No, because you have to have a centricity. So centricity. Okay, yeah. So the waveform problem is work in progress. And yes, again, you have to do the misaligned spins and the eccentric. So even if these were all green, you have to combine them. Okay, and then I'm going to very lately hand over to Marta. Sorry. No, I think it's you now. Okay, and we don't have this. Okay, so today's plan now is the next is going to be the mathematics. So I'm going to hand over to Marta. That was the kind of easy breezy overview. Here to go next. I'm going to... Oh, sorry. Is there any questions for Marta? No. Put it here on the drop. Let's get the microphone. Oh, here.
There's a clicker.
Wait, is there a lock?
No, there's a clicker.
Ah!
Theoretical physicist.
Is it just after this, right?
Okay. Thank you so much. Okay, so yeah, I'm Marta, as you heard before, and I took on this heavy lifting duty of just doing a big recap of all the equations that you have probably seen at some point, just a quick question. Have you all taken at some point differential geometry courses? Have you seen tensors in your life? Yes, all of you. So, okay, so I hope this is just going to be like a quick recap, just to put the equations that we are going to see into some context so that nothing sounds too strange or too exotic. Okay, so you all know that GR has this nice property of being formulated in a coordinate-independent way. And this is achieved by working with these mathematical objects that are called tensors. And we can think of tensors as generalizations of vectors and dual vectors. And dual vectors are the space of linear maps from vectors to real numbers. And you can have tensors with many indices, as you know. And these tensors establish a map between these product spaces to the real space. And the nice thing about tensors is that they transform into this Jacobian-like way that probably you've seen already many times. And so if I make a coordinate transformations, I can always express my tensor in my new system of coordinates just applying this Jacobian-like term. So another key concept that appears over and over in the equations is the covariant derivative. And then we can think of the covariant derivative as a sort of extension to curved spacetime of partial differentiation. So the thing is that if you just try naively to use the usual differentiation that you have in flat spacetime and curved spacetime, is not even transforming like a tensor, so it's not covariant, so it's not a nice differential operator if you want to keep always the same form for your equations. And this is where this covariant derivative comes in. Oops, I keep pressing the wrong button. So you have your usual partial derivative that you know from flat spacetime, plus, in this case, a connection term. And in GR, we usually work with a specific connection that is called the Levi-Civita connection that has some nice properties. And it's usually we call these symbols Christoffel symbols. And then you can see that essentially this covariant derivative transforms tensors, in this case, for instance, of dimension km to another tensor that has different dimensions, the dimensions of k and m plus 1. Okay, so let's just introduce some more tensors that we're going to see in the equations and in the following derivations. Now, you might have seen this sphere diagram here, where it essentially explains to you that if you try to parallel transport vectors in curved spacetime, then it becomes a bit problematic, because say you start from here, and then you try to keep your vector as straight as possible, and you go along the equator and then up to the North Pole, and then you're here. And then if you try to do the same along this other line, you get a different thing. So it can be confusing, because you'll be like, oh, okay, so then how can I parallel transport vectors in curved spacetime? And it turns out that there is a very nice operational definition of the Riemann tensor, this guy here, that is very important because it's the foundation of Einstein's field equation. And the Riemann tensor tells us exactly how a vector changes when we parallel transport it around a closed curve. So in other words, we can say that the Riemann tensor tells us about the lack of commutativity of differentiations in curved spacetime. So obviously in flat spacetime, these covariant derivatives would just reduce to partial derivatives. And then you know that partial derivatives commute in flat spacetime. So this would be 0. But in curved spacetime, the Riemann tensor is non-trivial. So you have that, in fact, you have to be a bit more careful with parallel transport in that case. We can also introduce through the covariant derivative other concepts that appear over and over. So we can take a vector, W mu, in coordinate notation, and we can say that it's parallel transported along a curve with a tangent V mu, if this equation is satisfied. And a special case of this equation is that a geodesic equation is this one, and it represents a curve whose tangent vector, u mu, is parallel transport along itself. So it's essentially the application of this formula when you just use the same vector in both cases. And sometimes you see these expanded in terms of derivatives with respect to proper time, and then you get this second order equation that you might see many times to describe geodesic motion in curved spacetime. So another important equation that we will see when we study the motion of test particle as when an incoming gravitational wave arrives is the geodesic deviation equation, is this here. And again, we can see that this exactly encapsulates the effect of curvature by looking at how two geodesic curves that here are represented by these two lines, gamma 0 and gamma 1, diverge if there is curvature. So obviously, again, we all know that if we have two, say, straight lines in flat space, there is no way that they will just diverge or converge in flat spacetime. But this is exactly what happens with the equivalent, say, of straight lines, roughly speaking, that is geodesics in the curved spacetime. So you can start off with this kind of construction for the derivation and consider two geodesics and then thread the spacetime between them with another family of curves parameterized by, say, S. And these other curves have tangent vectors xi. And then I can ask myself, okay, I have these two rods, these two geodesics, and now I kind of build a net in between them. And by studying the stretching and squeezing of this net, I'm just keeping track of, how much they converge or diverge just because of curvature. And it turns out that you can write this very nice and compact equation to describe these, which is telling you that, again, it's the Riemann tensor that is responsible, say, it measures somehow geodesic deviation in curved spacetime. So it's like having an inhomogeneous gravitational field because of, spacetime is curved, creates some kind of tidal forces, and these forces are measured by this tensor. And as I mentioned earlier, this same equation actually describes what happens in our detectors, because our detectors are acting in a similar way when a gravitational wave passes through the detector arms. They squeeze and squeeze and stretch pretty much like the ring of test masses that we see in textbooks. So this geodesic deviation equation is giving us both geometric and experimental insight of exactly what the effect of curvature is. Okay, so now we talked about a lot about this guy, the Riemann tensor. This is the explicit definition in terms of Christoffel symbols. And other important tensors or scalar in this case that appear later on are a contraction of the Riemann tensor. This is why it's so important, because from here you can derive all of the quantities that appear in the Einstein tensor, G mu nu. So then you get that you can contract two indices like here, and you get the Ricci tensor, and again you can contract further, and then you get the Ricci scalar. But everything comes from the Riemann tensor, sorry. And then you can build these other tensor here by combining these two guys. And this is exactly the left-hand side of the Einstein field equations. Okay, so then you might wonder, how do I derive the Einstein field equations in the first place? So this is a very generic way to go about this. That is through variational principle. So you start from an action where you have this Ricci part, that is your gravitational action, Einstein-Hilbert action, and then you can add a Lagrangian density here. That is your matter. This can be generalized, so the very nice thing about this formalism is that, say, you have a scalar field, you can put it here, you can build an action that makes sense for your theory, and you can apply the same variational principle and get the field equations in your theory that might not be, for instance, GR. So what you do is that you variate this action with respect to the metric, and then you get the form of the Einstein field equations that we know of. And the stress energy tensor that you probably are more familiar with is directly related to the matter Lagrangian density. So it's coming from here as well. So when I do this variation with respect to the metric of my action, then I get exactly the famous Einstein equations that we all like because they are giving us PhD studentships and jobs. This is also encapsulating the famous quote by Wheeler that says space-time tells matter how to move and matter tells space-time how to curve. Why? Because you see that essentially matter is sourcing curvature. But it's also the other way around. We, as we said earlier, curvature influences the geodesic motion and the motions of astrophysical bodies and everything. So the two pieces of the equations are deeply interconnected. Okay, as Anna said, there is a very basic way to go about the derivation of key concepts in gravitational wave theory, that is that of working with small perturbations of a flat spacetime. Okay, so we now assume that our metric is a combination of Minkowski spacetime plus a small perturbation that we take to be small in some sense. And then now we want to simplify as much as possible the Einstein field equation. So there are few tricks that we can play. So first of all, we know that because of covariance, then we can apply coordinate transformation, keep the physics quantum the same, but maybe transform our equations in a form that is simpler to solve. So we do this, and remember, we said tensors transform this way. So by simply taking partial derivatives of this transformation, I can get how the perturbation transforms. And from the definition of the Riemann tensor that we saw a few slides earlier, I just plug it in and then just keep linear order in H, I get how the Riemann tensor is expressed in terms of the metric perturbation. And then from here, we said we can construct everything, because once we have the Riemann tensor, we can get the Ricci, we can get the Ricci tensor and the Ricci scalar. So we are good to go. Okay, so something that is quite common also in the literature is to study this trace reverse metric perturbation, where I take the original perturbation and I subtract this term, so that the new perturbation has the inverse trace with respect to the original one. And then I apply a gauge condition that is very similar to what you have in electromagnetism. Is the divergence of, I require the divergence of my metric perturbation to be 0. And then if I do this, I can simplify my linearized Einstein equations to this form, which is very nice, because this is just a D'Alembertian operator acting on the trace reversed metric perturbation, and here is my source. So this equation is especially nice because it's a hyperbolic partial differential equation, so I know that it represents a well-posed problem. So solutions exist, are unique, and depend smoothly on initial data. Just a parenthesis, this is the derivation in flat spacetime, but the same formalism can be also used in curved spacetime, and you have a few adjustments. So here, this might be natural to conclude that this is transformation. Technically, it comes out because in curved spacetime, when you have to transform this guy as well, and then you pick up an extra term that is proportional to the derivative of the metric, which is flat in Minkowski, so you don't have it. And so this is the generalization of the partial derivative transformation with covariant derivatives. And the wave equation, likewise, becomes this guy. And this is almost like what we had before, replacing partial derivatives with covariant ones. But we also have this extra term here that will be 0 in flat spacetime, but is not in generic curved backgrounds. And so this, again, encodes some information about curvature. Okay, so as Jean-Baptiste mentioned at the very beginning, this is one of the key results of linear perturbation theory because it tells us that gravitational waves travel at the speed of light. And what's interesting also to notice is that, in principle, if you have a coincident electromagnetic gravitational wave observation, you could use it to test this because you could try and constrain the difference between the propagation speed that you get from the EM side with the one that you get from the GW side. And in fact, this has been done for the first BNS detection in 2017. Now we can say, okay, but turns out that if I look at my transformation, my coordinate changes of my gauge condition, the gauge condition, the transform in a very simple way. So my divergence of the metric trace reverse metric perturbation picks up this other D'Alembertian term. And so I can always stay within the Lorentz gauge where this guy is 0, provided that I set this other term to 0. So this is nice because this is giving me 4 extra equations to get rid of 4 extra degrees of freedom. So summing the 4 that I can just gauge away choosing an appropriate coordinates system. And then these ones that I can still play with, staying within the Lorentz gauge, then I essentially killed 8 degrees of freedom from a quantity that should have 10. So we already see that we are getting the right numbers of degrees of freedom that we expect, which would be the 2 polarizations of gravitational waves, at least in GR. Okay, so now I can say, okay, I can use these box D'Alembertian, this equation here. In fact, these are 4 equations because it's one for each index of the Xi vector. And then I can therefore impose 4 conditions to make my metric perturbation look very, very simple so that it's easier then to work with it. So the first common choice is to say, okay, I want the trace to be 0. And then I have 3 more. And the 3 more choices that usually are employed are that the time spatial part of the perturbation are set to 0 as well. And then immediately from here, it follows that if I use my Lorentz gauge condition, I can immediately see that because all of the time spatial parts are set to 0, then this also implies that the 0, 0 part, the time part of my metric perturbation is constant. So it's not related to radiative degrees of freedom. And later on, we will see that, in fact, a leading order, because then you can expand this metric perturbation in many, many orders. We will see that this term is related to the Newtonian potential of the source. So it's a static term. Okay, so now we said, nice, our metric perturbation is a wave equation, so I can plug in an ansatz for a plane wave equation. And then I also have my Lorentz gauge condition, and if I just apply this to this solution, then I immediately see that if the wave is propagating, say, along the k vector propagation, then this is telling me that the wave are transverse, because this is taking down a k factor here, so the product of these two guys is 0. We also know that we impose the metric to be traceless. And so from here, the most generic form that we get out, assuming, for instance, assuming that we discarded of all higher order terms, is this one. So we see that we can identify the remaining degrees of freedom that we mentioned before with the two polarizations, the plus and the cross. So the summary of all of this is that we have only two, and they are transfers to the direction of propagation that is indicated by this wave vector k. Okay, so now just a little recap of how we relate this to the geodesic deviation equation. We start from this expression that tells us how we can expand the proper distance in a free-falling detector frame, and we get some corrections that depend on the Riemann tensor again. And since the Riemann tensor, where we saw, involves derivatives, double derivatives, then it scales like 1 over L squared, where the L is the scale associated with the measured perturbation. And then it's always coming with factor of x, two factors of x. So we have corrections to the flat metric that scales like a small quantity. And then we can go back to our geodesic deviation equation and say, okay, if I assume that the elements of my detector frame are not moving relativistically under the passage of this gravitational wave, I can reduce my equation to a very simple form, and I can eventually write down everything in terms of the traceless transverse part of the metric perturbation, because if I look at this, I just use the definition, and all of the terms drops because, of gauge, Lorentz gauge, or because we said this part is static, for instance, and we are left only with this guy. So this is very nice because it immediately relates something that we saw at the beginning and it looked quite theoretical to something that is deeply connected to actually observables, polarizations of gravitational waves. And the classic standard example for this is that you apply this equation and you place a ring of test particles in, say, your XY plane, and you study how these particles are moved. So now you can suppose that initially they are forming a circle, for instance, and then you want to study how the circle moves when a gravitational wave arrives. So you just apply this equation, and you find that the passage of a gravitational wave induces these tiny displacements that are like harmonic in nature, and you can also write leading order here something that looks like an ellipse equation. But essentially, the semi-axis, semi-major and semi-minor axes are now stretching and squeezing because of the passage of these gravitational waves. And in this case, we simplify the derivation, just assuming that we just have a plus polarization for simplicity. Okay, so this would be the effect, but you will really see from the equation as well that this is what's happening at each instant of time. You have some deformation that, in this case, is sourced by the H plus polarization. Okay, so now you might be wondering, okay, what about more generic theories of gravity? Well, it turns out that generic metric theories of gravity admit more polarizations. In fact, they admit up to 6 polarizations. And not all of them are transverse. So if your wave, so here we have, again, rings of test particles in the xy plane, and imagine the waves propagating out of the board in the z direction. So now we are seeing how these different polarizations affect this ring of test masses. And here we have our friends, and we already know that these are transverse degrees of freedom. So the ring is only contracting and expanding in the xy plane. But then in more generic theories, we have also vector and scalar polarizations. And some of these are not transverse, in fact. Some of these are longitudinal. And you can see this because, here, for instance, you have x-z axis, y-z axis. And another way to see it is from this matrix here, where you see that you have some vectorial polarizations here. And you have also scalar polarizations, one of which is transverse and the other not. So another way to look at this is also studying the response of a detector to the passage of a gravitational wave. You can write down something like this, roughly speaking, where this is your data stream, then you have some noise, and then you have the response of your detector multiplying the polarization basis that you're using. And this is a kind of projection of, in the space of your polarization hypothesis. No? So you can always try to project your signal out of this manifold of your polarization hypothesis and see if the resulting null stream is compatible with pure noise. And this is a way to test if the signals that you receive are essentially pure GR polarizations, and it's already done, for instance, in LIGO-Virgo-Kara papers. Okay, so now we want to do some more simplifications. Just checking the time, okay. So the way you solve the source wave equation is by using Green's function. So the Green function, in this case, in four-dimensional space, looks like this one. So it's a function of retarded time, which makes sense because, signals don't travel at infinite speed. And then when you integrate the Green function against the source, then you get this expression. So this is the most generic solution to our source equation in linearized gravity. And now we want to see what happens to this seemingly complicated function if we suppose that we are observing a system from very, very far away, and our system is enclosed by a sphere of a small radius that I'm calling here epsilon. So let's suppose that we are sitting at a larger distance, much larger, called r, much larger than epsilon, which is the size of the source. Okay, so if we do this, then we can simplify this equation a bit, because we say, okay, let's suppose that we call this r. Distance from x prime would be variable inside where I have to integrate over the source, but we said it's a small sphere. And so I can just pull out this r dependence from here and simplify also accordingly the argument of my tensor. So now I can also apply some conservation equations, because we know that the stress energy tensor is conserved. And so we can write down these two equations separately, which would be just a specialization of the conservation equation to two different types of indices. So in one case, we choose a spatial indices as the free one, and in the other case, we choose the time one. And then we just write down the specific, explicit form of these divergence. And we know that this has to be 0. So now we play around a bit with Gauss' theorem, and we say, okay, we start from, for instance, this integral here. And we know by this conservation equation that it has to be equal to this other term. But now this is a divergence. I can just express this as the partial derivative acting on both terms, so on the tensor times xk. And then I can reduce that divergence term to just a flux type integral that goes away, because here I am suppose that I'm integrating this term only on the boundary of the sphere that is containing my source. There is no source there because I'm taking the boundary to be outside. So t mu nu is 0 there. And so I'm left only with what I get applying the derivative to this guy here, to the xk. And here I just get a Kronecker delta type contribution. So I'm left only with stress energy tensor. And I can play again this game with the other condition. So always trying to rephrase these sort of derivatives as total derivatives minus something else, using the usual linear properties of differentiations. And then I can, again, massage this other term into this one. So now the nice thing about these two equations is that I can now relate this double derivative that I can obtain by differentiating this guy one more with respect to time to this guy here because of this first equality. So I'm taking the derivative here, right? And then I'm just getting this through the first equation. So this is a way to derive what is known as the quadrupole formula. And the quadrupole formula is very useful because it's telling us exactly how the metric perturbation is related to time derivatives of this quadrupole moment tensor here. Okay, and it died. And in terms of the metric perturbation, I can, sorry. In terms of the metric perturbation, I can define other quantities that have physical meaning that are, for instance, the energy flux in terms of always the traceless transverse tensor that I just introduced. It turns out that more generically, so you can play this game and go up to higher orders and re-express all of these terms that you will get out from the integral of that we saw earlier in terms of momenta of the stress energy tensor. So integral of the types that we saw earlier for the quadrupole moment, mass moment tensor. And you get a very, very long expansion where you can go up to higher order. And each order is suppressed with respect to the previous order by an inverse power of the speed of light. So this is telling us that what we obtained earlier is just the leading order term of an expansion that goes on for many higher orders. And the higher orders contribute less and less to the final result. Different radiative multiple moments contribute to the metric perturbation, and what we got, the quadrupole, is the dominant one. Okay, so what we get, for instance, if we go to next order, we get other terms that are just higher momenta, mass momenta, or different types of integral that are called current type multiples. And this is just a schematic expression of the next order. This would be, for instance, the mass octuple term, which is just higher momenta of the time component of the stress energy tensor with just more powers, more x variables in the integral. And what we said at the beginning, if we look at this form, we can see that we can ask ourselves, oh, what about the L0 and L1 modes, multiples, sorry. And we say, for instance, that in the case of L0, we get a term that is like this in the H00 component. And this is just essentially something that reminds us of the Newtonian potential that we have in classical mechanics. So these two terms, these two orders, multiple orders, do not radiate because they are just associated with parts that are static, or I can always gauge away. For instance, the L1 multiple is related to just linear momentum, and I can always put myself in a frame where linear momentum is 0, and I also know that I have mass and linear momentum conservation in GR, so I know that those terms should not radiate. So now there are some more technicalities that I will just briefly mention, but to recover the traceless transverse quantities, remember that we had this matrix that had a specific form where our polarizations were appearing. So when we do the derivation starting from the momenta, we have to then project somehow the metric in the way we want, so that the final metric perturbation is traceless and transverse. And we can do this by introducing some projector operators like this. And so the final expression would be involving these projector operators acting on the results that we show in the previous slide. And likewise, we can also play the same game at the level of the multiples themselves, because we know that we want something that is traceless and transverse, and we can just introduce these versions that are called STF multiples moments. Okay, so now you might be wondering, okay, we have worked in first order in linearized gravity. What happens if I go up and include more orders in H? So at higher orders, it turns out that my source term becomes more involved, because essentially, because of nonlinear interactions of that I get, because GR is nonlinear theory, I get some contribution from here that is just coming from that thing. Even if I don't have an actual source, I get some terms in the source term that are just result of nonlinearities in the theory. And I have also other terms that are gauge terms that I have to put there in my source, or I can put there in my source, to make sure that the gauge condition is respected of every order in perturbation theory. So if I go up, in fact, the source term is becoming a slightly different object that is called stress energy pseudo-tensor, because it has more terms inside that are not just the source term that we saw initially. So we can apply all of the stuff that we have seen before. So now we know that we can, at leading order, our metric, spatial metric, is sourced by the mass quadrupole moment. And we can just apply the definition what we saw earlier to derive the metric perturbation as a function of a density, for instance, of a stress energy tensor that we assume. We can start, for instance, for two masses on a circular orbit, and we can just assume that they're point particles. So I can write the density in this delta form. And then just applying the definition of quadrupole mass moment, then I can obtain this term, and then I can take 2 times derivatives. I know that this is the definition that we saw earlier to get the plus and cross polarization. So what do I get if I do all of this? Okay, so I can consider, we said earlier that we have to project our metric perturbation And we have to specify a wave frame. So we have to establish the direction that is linking the source and the observer. So if I do that, then the polarizations are going to take on a dependence that encodes information about the relative position of this vector that is linking the source and the observer, and whatever vector I use, for instance, in my calculation, because, for instance, in the circular orbit case, I might just choose to align the z vector for my calculation with the normal to the orbital plane, just because it makes calculations much easier. But that z direction doesn't coincide with the direction from the source to the observer. So now I have to do this conversion. And when doing this conversion, if I imagine that I call iota the angle between z prime, which is the direction from source to observer, and z, which is the original axis that I use in my derivation, in my source frame, what's called, then I can do the projection to get my observed polarizations. And I get this expression, which is quite telling, because if we had some masses that were performing a motion with orbital frequency omega, these equations are telling us that the polarizations have, in fact, twice as much that frequency, which is something that we know. And this is just a leading order term. We also have a dependence on the inclination, which we know with respect to this symmetry axis, z-axis of the source frame, that we will comment a bit about later. But we already said that we can expand these metric perturbation into higher radiative multiples, and we will get new types of terms that will contribute with higher characteristic frequencies. And so if I arrange all of these terms in an expansion into spin-weighted spherical harmonics, which is the expansion that is normally used for waveform modeling, for instance, data analysis, then I can group all of these contributions that are coming from higher orders in my expansion into what are normally called higher modes, higher harmonics, and these are very important, especially when you have high SNR signals, but already in LIGO, really, because depending on the inclination they can of the source, they can give a significant contribution. But now we are working with this very simple approximation where essentially we're keeping only the mass quadrupole term, leading order term, and essentially we are getting the 2-2 mode-like contribution in terms of spin with spherical harmonics. And we can see from here that depending on the orientation of the source, we get also different polarization content. For instance, if iota is 0, so if my source is face on, then the two polarizations have the same amplitudes. If I have an edge-on source, this guy just goes away, so I have linearly polarized waves. But in general, I can expect that I will have a mixture of these two guys, and hence my signal will be elliptically polarized. You can also think about the more general situation where this angle is not actually constant because, for instance, the source is precessing. So in that case, the z-axis in the source frame will move around, and this iota angle would not be constant. So this would give some extra modulation to the amplitude of the waveform that can also be leveraged to understand the orbital dynamics of the source. Okay, so I mentioned earlier that it's quite common to do this expansion in spherical harmonics, and these higher modes encode some higher terms that we haven't explicitly seen in the multipolar expansion. And again, we mentioned this, that also in this expansion, it's implicit that we choose a radiation source frame for the definition of these angles. So one has to always be very careful when working with data to understand exactly what the source frame is of the model because some models don't do the conversion for you, depending on the waveform interface. So one has to be careful. So the 2 mode, 2 and 2 modes tend to be dominant. But you can see from here that you have also this weighting term given by the spin-weighted spherical harmonic that will give you an inclination dependence of the relative strength of the higher modes. On top of that, you have to consider the sheer amplitude of the modes themselves. It tend to be smaller, but depending also on the properties of the source, it might be that some of the higher harmonics are stronger or weaker. And this is something that has been looked at widely for design, essentially, to understand how many higher harmonics we need to model accurately so that we don't incur into biases. And this is exactly what I was saying that earlier, that in the end, from your polarization, you want to build a detector response. So you can just combine your polarizations with a certain antenna pattern function. And again, this is just to stress that you need to make sure that you always aware of these different frames that are used in waveform modeling and data analysis, and so source frame versus wave frame. And again, just the last few slides, 2 slides for concluding. We saw in the derivation of the polarization sourced by circular motion earlier here, that we had these simple expressions in terms of the reduced mass because we were working with test particles, so we were simplifying a lot of physics. But when we work with astrophysical sources, you don't want to work with reduced mass, you want to work with this other quantity that is called chirp mass. And just by plugging in into the equation that I showed earlier, then you get the scaling of how gravitational waves amplitude behave with respect to mass. You also get some other results. In an expanding universe, you have to go from your naive radial separation to a quantity called the luminosity distance that takes into account the fact that the universe is expanding. And so this radial distance becomes something slightly more complicated. And the more generic expression is this one for the luminosity distance. You see is also a function of your cosmology. So for actual observations, if you measure the luminosity distance, you can always go back to redshift. But this implies that you're assuming a certain cosmology under the hood. And likewise, the observed mass parameters that we are detecting, for instance, today with the LIGOs and Virgo, they are redshifted accordingly. So we're not measuring source frame masses, but we're always measuring redshifted quantities. Okay, so this was a very fast introduction. But I am going to upload the slides. So if you want to look again at the derivation or anything that was not enough time to do, you can look at that. Okay, so this is just a recap of the next topics that you're going to see. We are going to see post-Newtonian framework, gravitational self-force, black hole perturbation theory, numerical relativity, and finally how you combine all of these guys together to do spiral merger ring down waveform models. Okay, so I'm almost
Yeah, thanks a lot, Marta. I think we have a couple of minutes for questions, if any. Yeah.
Thank you. So so a couple questions. First, could you summarize the reasoning for why GR only has 2 polarizations? Mm-hmm. And second, is there an intuition for why the 2 modes are dominant from, people say they are dominant for most sources? And
Yeah,
like when that breaks down, in which conditions do you have to take into account the higher modes?
Yeah, so the two polarizations you've seen from derivation essentially, that you know, just by working with the equations, and then when you gauge away all of your degrees of freedom, you're left with these two degrees of freedom. And you can think of them as, if you think about it from a particle physics perspective, you can think of them as the degrees of freedom of a massless spin 2 particle, for instance, if you want to look at the graviton perspective.
Okay, so you start with an equation with like 10 components, 10 tensor components because it's symmetric, and then you eliminate 4 because of gauge freedom. And but you eliminate 4 for...
Because the Lorentz gauge has these extra... So you can think about some of the equations define some constraints, and some of the equations define your coordinate freedom in a way.
Okay.
So this is something that you find in NR, for instance, as well. There is a similar situation. But the thing is that here you really have these spurious degrees of freedom that you can always, you can only kill if you evolve the field equations and your constraints or your gauge conditions together. Otherwise, you get stuff that is not really physical.
Okay.
And yeah, the question, so you get it from, again, when you do the expansion of the metric perturbation that we saw earlier, you get exactly that, you know, the leading order term has this form, and when you do the re-expansion into spherical, spin-weighted spherical harmonics, that's the 2-2 mode contribution.
Okay, so that is L equals 2, that is, I guess, quadrupole, and then M equals +1 + 2, that's a specific term inside the quadrupole.
Yeah. That's just the magnetic index of the spin-weighted spherical harmonics. But it's the same, essentially. It's the same order of magnitude contribution for, at least for these aligned spin cases.
Okay, so I guess my question is just having a simple intuition for when we need to take other modes into account.
No, there is no such thing. Because, as I said, there are two factors that enter this game. Oh, here. Okay, so there are two factors that enter this game. The fact that if you just look at the amplitude, say, look at just the amplitude of, I don't know, numerical relativity modes, with respect to the 2-2 mode, then you will see that the relative amplitudes of these HLNs with respect to the 2-2 mode varies if you vary the mass ratio, for instance, if you vary the spin. So there is no constant ratio between these two amplitudes that tells you, oh, it's always the case that I can do without the 2-2 mode, I can do without the 3-3 or 4-4 mode, because you really have to do a parameter space study. And depending on the parameters of your source, you will have these amplitude ratios vary. So it's really source dependent. And the other thing is the spin-weighted spherical harmonic part. Because this is telling you, for instance, that it's a source is face on, then this is going to kill a bunch of odd modes, for example. Because if you work out how these spin-weighted spherical harmonics behave with respect to N and L, then you will see that there is a pattern, and depending on the source orientation, sometimes these higher harmonics are excited, sometimes not, and so you have to really not only consider the intrinsic parameters of your source, but also where the source is on the sky and how the source frame is inclined with respect to your observer, because that could mean that some harmonics are completely negligible and or not.
Thank you.
Another hand up.
One last quick question, maybe 1 minute.
Yeah, I don't know if it's a long or short question, but I don't know. I'm super I couldn't find any paper that actually tell me, for example, for a given event that's been seen by, let's say, 3 detectors, the actual polarization coefficient, like if it's an ellipse, if it's circularly polarized or linearly polarized. So how come that doesn't exist? Is it too hard? Is it because we're missing Cagra right now?
No,
yeah.
no.
What's the?
No, I mean usually, I mean it's very complicated. In the full case, it's not that that easy to define the polarization of the source, because you have also that if you sum all of the harmonics, for instance, and you try to take coefficients like this between the two, you know, even if you wanted to do some leading order ratios of the relative amplitudes of plus and cross, it will be even more dependent from the type of spherical harmonics amplitude that you get. So in general, you have that the waveform is elliptically polarized in a way that is not really easy to decompose in plus and cross, because you have a lot of terms contributing in the spin-weighted spherical harmonic expansion.
And so will we ever be able to constrain it?
I think so. I think for the science that you want to do, because also the polarization is depending on the wave frame. So it's what for the science that you want to do, I would think that it's really you want to really make sure that you have 2 polarizations and not more. But how they combine exactly between them, it's also frame dependent, wave frame dependent. So it's not really something that is necessarily super important, or I don't know, maybe not. You know, maybe that tied to fundamental physics questions.
Okay.
Okay, maybe let's wait. Let's thank once again the speakers of today. I think it's time for lunch. Those who haven't watched their cups, please do it quickly before going to lunch. And the icebreaker will be at 2. And for those who want to participate, we'll just meet just in front of the lecture room, right, where you took the coffee break.
That's very quick.
Oh my! I have to rush through all the equations.
It's okay to leave. I mean, the rooms are all set.
You know what I'm saying? Like, there's things that you
There's no one else.
touched on that we're going to be having another.
Yeah.